in, sorry, the subgroup A is suitable in G. So you can see this in various ways. For example, you can just construct, so you can use the action of A on a hyperbolic space, which proves that it's acylindrically hyperbolic, to construct an action of this free product on some sort of tree of spaces, which is still acylindrical, and the space, this tree of spaces is hyperbolic, and A will have non-elementary action. Or there is a slightly easier way, which uses the notion of a hyperbolically embedded subgroup, which I haven't introduced yet. That's the topic of the next lecture. But anyway, believe me, just believe me that that's something which is sort of easy to verify. And now if you know this, that this is acylindrically hyperbolic and A is suitable, well, in the definition of suitable, you also have to verify this condition, second condition, as doesn't normalize any finite non-trivial subgroup. So non-elementarity is easy to prove, and this is obvious from the free product structure. So now you just take the quotient, so you apply theorem, let's call it somehow, theorem 1. There will be no other numbers in my lecture, but let's apply this theorem 1 to the group G, to the suitable subgroup S equals A, and the finite subset T, which is C1, Ck, and I also have to specify X. So when you prove that this group is acylindrically hyperbolic, it's easy to show that you can include H into the set of generators. Well, for example, if you have an action of A on a hyperbolic space, and you want to find an action of G on a hyperbolic space, and you use the tree of spaces approach, then you somehow compose the action of this free product on the bus serve tree with the action of A on the original space. And H stabilizes a point on the bus serve tree, which means that if you pass from this action to the set of generators via the standard Newman-Schwarz argument, H will be included in the set of generators. So this is something which is very easy. So you apply the first theorem, and what you get immediately is you get a quotient Q such that, well, first of all, Q is a quotient of the original group A. Not only it's a quotient of G, it's a quotient of the original group A. Why? Because of this condition. So Q is generated by epsilon of T, the image of T, and epsilon of A, right? Because G is generated by A and T. T is the generating set of H, right? Here. A, well, that's obvious. So the image, the quotient of G will be generated by the images of T and A. But now we know that epsilon of T belongs to epsilon of A by this condition number 3. Okay. So this is generated by epsilon of A, which means that it's a quotient of A. Okay? That's a quotient of A. And H, which sits inside the wall of radius 1 in my group, so I apply the theorem in the case when capital N is just 1. So this one is not the same as this one. This one is the identity element, and this one is number 1. So H sits in this wall, so by condition number 2, the restriction of my homomorphism onto this ball is injected. So which means that epsilon restricted to H is injected, i.e. H embeds in. So that's it. That's the end of it. So as you see, you don't need to know anything about small cancellation to use this. So why is this interesting? Well, first of all, it says that every acylindrical hyperbolic group is very large in the algebraic sense. But let's try to see what it gives us for some particular classes of acylindrical hyperbolic groups. And I want to give you just one application to mapping class groups. So for mapping class groups, there is a theorem which is proved in my paper with François Damani and then some Girardel. Which says that if G is a subgroup of a mapping class group of a surface with genus G and P punctures, no restrictions on genus and punctures, then either G is virtually abelian or G surjects onto an acylindrically hyperbolic group. So how you prove that? You take a subgroup in a mapping class group. If it contains a pseudo-Anosov element, then either it is virtually cyclic, in which case it's virtually abelian, or it's not virtually cyclic. If it's not virtually cyclic, then it is acylindrically hyperbolic, because this pseudo-Anosov element is a WPD element with respect to the action on the curve complex, or, well, you don't even need WPD, the action is acylindrical, so if the group is not virtually abelian and contains an alexandronic element, as you remember from equivalent characterizations from this classification of actions, acylindrical actions, which I explained last time, the group must act non-elementarily, so it's acylindrically hyperbolic already. Done. Now it remains to consider the case when G doesn't contain a pseudo-Anosov element. But in this case, it's reducible, so there is this Ivanov theory, and then you just pass to smaller subgroups. So when it's reducible, it's a product of mapping class groups of smaller complexity, maybe with boundary components, but somehow do the induction and you prove this result. Now here's a corollary of this. For every subgroup of the mapping class group of a puncture closed surface, so every subgroup is either virtually abelian or SQ universal. Why is that? Because of this theorem and the theorem I just proved. If it's virtually abelian, it's virtually abelian. If it surjects on an acylindrical hyperbolic group, then it's SQ universal. Because every countable group embeds in the quotient of this group, therefore in the quotient of this group, right? So this doesn't sound like a very exciting result, but it implies, for example, several results previously known for mapping class groups. For example, it implies that its alternative, which is proved by Ivanov, which in this case says that every subgroup of a mapping class group either contains a free subgroup or is virtually abelian, right? So this is much stronger. It's either virtually abelian or SQ universal, and as I explained, being SQ universal means that the free subgroup is there. And another thing which immediately follows from this is that for every homomorphism from SL3Z to this subgroup G, every homomorphism of this sort has finite image. You can replace 3Z is my abbreviation for an irreducible lattice in a semi-simple, connected semi-simple V group with finite center. Okay? So that's the class of lattices to which Margulis theorem applies. And this, there are several proofs of this result. The first one was due to Farr and Meizu. And then there were several subsequent proofs. So we immediately get it from here, because if SL3Z maps into this, so let's consider, suppose we have a homomorphism like this. Let's consider the image. Okay? So this group has only countably many normal subgroups, as we already discussed. So the image cannot be a skew universal, right? Therefore, the image is virtually abelian by this corollary. But it's fairly easy to see that every virtually abelian image of this group is actually finite. That's an exercise in elementary groups. Okay? So you get this, and you get some other results, of course. Well, this is the first application which I want to talk about. Now, the second application which I want to talk about is to constructing some sort of monster groups. Well, there are lots of constructions of groups with strange properties in group theory, and many of them can be done by using small constellation in acylindrically hyperbolic groups. What I want to explain how to answer the following question, which was open for quite some time. Does there exist a finitely generated group where all non-trivial elements are conjugated? The answer is yes, of course. So first of all, the trivial group, right? Second, the group Z2. Other than 1 and Z2. Well, kind of natural question. I mean, in group theory, we want to impose some sort of finiteness conditions. For example, that the group is torsion, it has something finite, and then we want to ask, well, does there exist an infinite group with this property? So this is one of the questions of this sort. It was open for quite some time, and it's a difficult question. So the first observation, it's a remark which I leave as an exercise. Such a group must be torsion-free Well, this is, the hint is that you have to use the little Fermat theory. So first observation is that all elements are conjugate, therefore non-trivial. Therefore, they all have the same order, so the order must be prime, and then every element is conjugate to its square. Well, enough hints. The little Fermat exercise. So then, a consequence of this remark is that such a group, let's call it G for brevity, G is not a limit of hyperbolic groups. What do I mean by this? There are several constructions in group theory, including the construction of the Burnside groups, three Burnside groups, which Mark mentioned in the previous talk, which go like this. So you start with some group G0, say the free group, and then you construct a sequence of homomorphisms, like G maps onto G1, G1 maps onto G2, and so on, where all these groups are hyperbolic, and then you take the direct limit of this sequence, let's call it G infinity, which is your group G. In this case, we say that this group is a limit of hyperbolic groups. If you get your G, normally you get such a group by imposing small cancellation relations at each step. So you check that every group in this sequence at every finite step is hyperbolic, and you say that this group is a limit of hyperbolic groups. There are lots of constructions of monster groups along these lines. For example, three Burnside groups, Tarski monsters constructed by Olshansky and many others. Now, such a group G with two conjugacy clusters cannot be constructed in this way. Why? Because let's fix some element A in this group. And you know that A is conjugate to its square, right? Because all elements must be conjugated. So A, say, there exists AT such that T inverse AT equals A squared in my group G, right? But this is just one relation, so if it holds true in this group, it must hold in some GI, right? On some finite step. Now, such a relation is impossible in a hyperbolic group if A has infinite order, right? As we observed by this remark, this group is torsion-free, so A has infinite order. And if you have such a relation in a hyperbolic group, it's impossible. Why? Because if, in this situation, the subgroup generated by A becomes exponentially distorted, right? And this is impossible in a hyperbolic group. Moreover, it's known that in a hyperbolic group, if an element of infinite order is conjugate to its power, then this power is either plus or minus 1. Well-known result. So what it means that you really have to go beyond hyperbolicity. Right? There's no way you can get it with hyperbolicity. So that's why I wanted to mention this. Now here's a construction which should say cylindrical hyperbolic group. So the theorem I want to show is that the answer to this question is yes. And originally it was proved in my paper more than 10 years ago. I didn't use acylindrically hyperbolic groups, but I did use relatively hyperbolic groups, which is the first step beyond hyperbolicity. Now the construction with relatively hyperbolic groups is still a little bit technical. With acylindrically hyperbolic groups, it's just extremely easy. So the proof, which I'm going to present, is borrowed from the paper by Michael Hall. And the proof is the following. So let's take G to be the free group on two generators. And that's my group G0. Okay? Now this is, of course, acylindrically hyperbolic, right? And then I construct a sequence of groups and homomorphisms like this by induction. So my inductive assumption is assume that Gn is constructed already for some n and satisfies the following conditions. So this is my inductive assumption. First of all, Gn is acylindrically hyperbolic. Second condition, well, let me enumerate all elements of G0. So let's say G0 equals 1, G0, G1, and so on. Okay, I enumerate all elements, countable group, I enumerate all elements. So I also assume that G0, G1, G0, and so on, Gn minus 1 are conjugate in G sub n. Third condition is that Gn is torsion free. Okay? Another exercise is to verify this for the free group. So free group is acylindrically hyperbolic, right? Thanks to the enumeration I choose, this is true. So this just says for n equals 0, let's say Gn. For n equals 0, it just says that G0 is conjugate to G0, no doubt it is. And the Gn is torsion free, right? Free groups are torsion Right? So now you just construct the group Gn plus 1 in 2 steps. So first you construct the group, let's call it Gn plus 1 half. It will be the group Gn, and Hn an extension of the group Gn. So you add one generators, the stable letter of the Hn extension, and you conjugate G0, so T inverse, let's start with Gn plus 1. You conjugate Gn plus 1 to G0. Well, you have to be a little bit careful here. It can happen, so by Gn plus 1, what I mean is the image of the element Gn plus 1 in my group Gn. It can happen that this image is already a trivial element. Then I just do nothing. Then in this step, I just take Gn plus 1 half to be, then I just take Gn plus 1 equals Gn. That's it. So, let me say non-trivial elements from this set are conjugated to Gn. Of course, some of them may become trivial at some steps, and that I don't care about, because only thing I want is to have all trivial, non-trivial elements. Okay? So, it turns out that this group is acylindrically hyperbolic, so this is similar to the verification of acylindrical hyperbolicity condition in the proof of SQ universality, which is here, when you take the free product. So here you do the similar thing. You can either use Basser tree, or you can associate with this Hn extension, or you can use hyperbolically embedded subgroups, which is a little bit more difficult and a little bit easier, but more technical. So it's acylindrically hyperbolic, and the subgroup Gn is suitable. In Gn plus 1. And then you just take Gn to be the quotient Gn plus 1. To be the quotient of Gn plus 1, where Q is, well, Q is given by theorem 1 applied to the group G, which is G1 plus 1 half, the subgroup, suitable subgroup S, which is Gn, the set T, which consists of the stable letter, and that's it. So now what you get is that this quotient group is acylindrically hyperbolic. Here it is. It's a quotient of the original group G, and that's because of this third condition, because you artificially force this element T to become an element of the image of S. So it's a quotient of G, and then you get the torsion-free condition from number 4, right? So all their inductive assumptions are proved. And then you just take the group G, which is G infinity, which is the limit group in this construction when you impose all these relations. So what you get, it has exactly 2 conjugacy classes. Which means the trivial element and all non-trivial elements are conjugated, right? The only thing, of course, is to show that this group is non-trivial itself and is not Z mod 2Z. But if it's finite, I don't care if it's trivial or Z mod 2Z. If it's finite, then it is finitely presented. Which means that all relations of this group will hold true at some finite step. Then it means that at some finite step you get a finite group. That's impossible, because at each finite step our group is a cylindrical hyperbolic. End of the group. Well, that's all I wanted to talk about today. So next time we will talk about the things related to hyperbolically embedded subgroups.
Any quick questions for Dennis? Yeah. Do you think you can use this technology to construct Osin?
unbounded torsion, then yes, that was done a long time ago. But you don't need a cylindrical characteristic for that. If you think about bounded torsion, then it's much harder. It's not so easy. I mean, there is no lazy version of this model. But it can also be done using acylindricity, and I think this is what Emile Coulon is going to talk about tomorrow. Where's Emile?
Yeah, you can make a quotient where you cannot do anything about the elliptic subgroup, that's fine, but all the rest, more or less, becomes has finite order at the end.
Oh, but this is much more complicated theory. There is no such an easy, it's more difficult. There is something we have.
Okay, let's thank Dennis again.